All right. It's 5 p.m. Central European Time. Let's start. Let me unshare this. Okay. Welcome everybody. It's a big pleasure to start this series, the DinAmicI or DinAmicI internet series of seminars. And I see there's a whole lot of us and a lot of participants, and it's I'm very happy to report this. And today's speaker, the first speaker of this series, will be Giulio Tiozzo from the University of Toronto, whom we thank very much for accepting to be our first speaker of the series. Giulio is a longtime friend. He graduated from Scuola Normale Superiore in Pisa in Italy in 2008, then went on to pursue a PhD in mathematics at Harvard University under the direction of Kurt McMullen in 2013, and then he went to Yale University as a Gibbs assistant professor, and he's been for a number of years, I don't know exactly how many, at the University of Toronto as an assistant professor, if I'm not wrong. Right, Giulio?
Correct.
And thank you very much for joining us and for giving this talk, and I'll give it up to you.
Okay, so thanks very much for the invitation. Yeah, it's very nice to be here among lots of former friends and new friends, and it's also nice to be close to my home country, because we've been in a very difficult situation in many countries, but especially in Italy. So it's kind of nice to be all together, even though we're kind of apart. But anyways, so what I'm talking about today will be some new central limit theorem. Of course, the central limit theorem is a very famous theorem in probability and dynamics, and it has lots of applications and various variations of it. And so we will discuss some form of a more general central limit theorem for certain group actions. So it will have some geometric flavor.
Giulio, before you start sharing your screen and beginning with the actual talk, let me just say that if everybody wants to ask questions, they can just say so in the chat line, and then I'll stop Giulio, and I'll open up, or somebody will open up your microphone, and you can actually speak your question. Thank you very much. Sorry about that, Giulio.
Okay, great. Okay, so I guess I'll start sharing my screen. So presumably you should already see the title. So as I said, the title will be Central Limit Theorems for Counting Measures in Coarse Negative Curvature. So of course, most of you have some idea what central limit theorem means. We will, of course, be more precise. And basically also the central limit theorem depends on what kind of measure you're considering. So there are many measures that have geometric interest. And for us, we will talk about counting measures, and our setting will be manifolds of negative curvature, and not just manifolds, but graphs and other structures of a similar flavor. And okay, so how do I? Okay, so I will start with actually part of the motivation came from some experimental results that came up in around 2013 or something like that by Chas and Lally, and then Chas-Li-Maskit. And this led us, this led them to formulate certain conjecture, which is some form of central limit theorem. And I will discuss that. And then, in fact, we somehow in joint work with Sam Taylor and Ilya Gethman, eventually we did settle this conjecture. And so I will discuss that part, but then I will go to more recent results, which are kind of a more general flavor. And maybe if you read the abstract and you're a bit more into the technical part, one main point is that we will kind of get rid of some limitations that usually come from the thermodynamic formalism approach. So it will be a slightly different flavor of approach for us. So as I just mentioned, this is all joint work with Ilya Gethman and Sam Taylor. Okay, so first of all, let's start with a statement of what Chas-Li and Maskit considered. So first of all, they have some a hyperbolic pair of pants. So basically, I just have a manifold with 3 geodesic boundaries like that, and it has maybe 3 lengths, A, B, and C, and then you can take a geodesic on this manifold. For instance, we will call it a geodesic gamma, and tau of gamma will be the length of such geodesic. So this is a very nice and classical geometric object that you can look at, and you can look at how the length are distributed. So if you take some notion of randomness, and again, there will be perhaps several notions of randomness, but we want to know how this length would be distributed. So let's keep going. So basically, so what is the setting? Well, the setting is that if you have a hyperbolic pair of pants, the fundamental group would just be a free group. So free group obviously has many possible choices of generating sets, but I guess the most standard, let's take the most standard one. And then it's well known that the closed geodesic on such a manifold is corresponding to a conjugacy class in this group. And then we start already seeing what are the 2 main characters of today's talk. Will be 2 types of ways to measure the length of a geodesic or a conjugacy class. So one of them would be just what's called the word length. So what is word length? Word length is you take group element and you write it as a sequence, as a product of generators. So now how many generators do you need? Well, the minimum number of such generators that you need usually is called the word length. So of course it depends on this generating set. So this is a very combinatorial concept of length. But of course it has also some geometric flavor, because you can think of the group as a graph, and somehow this word length would be the length of this graph. So, and also if you have a conjugacy class, so not just one group element, you can take the minimum over all the representatives of this conjugacy class, and you get the notion of length for this conjugacy class. So this is the combinatorial length. And then there's the notion of, say, hyperbolic length. So hyperbolic length is just the length, the actual length in the actual manifold. So this is again, manifold with constant negative curvature. It's a very nice Riemannian manifold. So this geodesic is a closed loop and it has notion of length. So we will denote this length as tau. There's also another reason for doing that, but we will see it later. Okay, so now what did Chas-Li and Maskit do? So again, they looked at this distribution of these geodesics under certain notion of randomness. And again, there are several notions of randomness. So what they did is they plotted this kind of picture. So what did they do? So basically, you take this combinatorial length. So basically, you take all the words in your group of a certain length, right? Say here it's a length 100. So you have, of course, the group has exponential growth. So you have many, many words of length 100. And for these words, you can associate a geodesic on your manifold, and you can think of the length of such geodesic. So then that's what they plot. They plot this graph is exactly that. So you take uniformly at random 100,000 words of word length 100. And then you plot on this axis, so y-axis is the length in the geometric sense. And so you see immediately that you get some sort of Gaussian distribution. So of course, this immediately suggests that should be central limit theorem at play. And of course, what you could do many things, and you can also fiddle with your parameters. We're not going to be super interested in that at this moment, but you certainly could do that. And in particular, Chas-Li and Maskit, they consider this in particular. Here, there are certain different notions, different values for the parameters. So here's this 1, 1, 1. So meaning that the 3 cuffs, the 3 boundaries have the same length. And then this one, 0.111, means one cuff is much smaller. And then this has one with length 10, so one cuff is much bigger, the other one is much smaller, the other in the middle. And so you also could be interested in how this is kind of distributed. And in fact, one thing that you can notice immediately is that if these 3 cuffs are kind of very different from each other. For instance, one of them is length 0.1. Well, the distribution basically eventually will still be Gaussian, but it's gonna experimentally is gonna be harder to produce the actual Gaussian because there will be much more of an error. And we will see later that this is kind of related to the variance of this Gaussian. So this is the pictures that they produced, and then there's other pictures which are other same phenomena. So here they show, again, basically they show the convergence to this normal distribution just by checking different lengths. So here you start with all the words of length 14, and then you see that well, you have some distribution which is not so easy to figure out, but then when you increase the number of the length, then you see 20 of them, so you see many more elements, and you average, and eventually 50, and then 100, and you see with 100 it's much more recognizable that you have actually a kind of Gaussian curve. So these are kind of the original experiments that they did, and so they wrote this paper, and they kind of formulated the conjecture. And also there's also something similar that Chas and Lally did a few years before that, which is also of same flavor, which is instead of considering length, hyperbolic length, they consider intersections. So basically here you take a curve in your surface and you look at how many intersections there are of the curve with itself. So this is self-intersection. And again, if you sample these curves uniformly at random using the uniform distribution for the word metric, basically, again, you see this Gaussian distribution. And in fact, this was not a conjecture. In fact, Chas and Lally wrote a paper where they actually proved rigorously this result. And so this was sort of one of the first starting points. And then they went to this other problem, and then they formulated this conjecture. Are there any questions so far? Okay, so.
No questions in the chat so far.
Okay, good. But you can see everything right? Okay, very good. So basically, yeah, so let me formulate what was the conjecture that I had, precisely what you saw in the pictures, basically. So formally, again, you start with this manifold with, for instance, is a pair of pants. It could be also some other surface. And then you take the fundamental group of that surface, and you can pick randomly geodesics by picking conjugacy classes in this group. And you pick, again, you have these two lengths, the word length, which is combinatorial, and the hyperbolic length, which is geometric. And then you want to say, how do they compare, basically? And the idea is the following. You take randomly you take the set of all words of length n, and you take a uniform distribution there. You get a measure which is called lambda n. And then, so it should be lambda n here too. Yeah, so lambda n is this measure on the set of all words of length n. And then you just look at how many of these words have a given geometric length. So tau gamma is the geometric length. And again, there's a main term which is linear in the number of steps, and then if you divide by square root of n, you get the usual Gaussian convergence. So if you look at how many there are between IA and B, this converges to the integral of the Gaussian measure between A and B. So this is a very, in a way, simple to state conjecture. And of course, whenever you have a phenomenon of this sort, we will say you have a central limit here. So in fact, we did prove this conjecture in 2018, and so somehow, yeah, we were already studying similar objects, and so somehow it was kind of, we had the right tools somehow to do it. But basically, this is not what I want to talk about here today, because what the main gist of what I'm talking about today is a generalization of this result in a sort of far more general context, because basically when we proved this result, still we were using, in a way, the classic thermodynamic formalism approach, which basically uses Hölder continuous functions and uses some coding with some shift space. Again, there will still be coding with the shift space today, but it will be different. And then in particular, this type of methods work in this context because the group is very nice. It's a free group or surface group, and the action of this group on the universal cover is also very nice. It's co-compact, for instance. And the space also is very nice as uniform negative curvature. So this is a much nicer situation. But in fact, we will go beyond this setting, and we will present a few more geometric applications which require this new setting. Okay, so this is basically, so of course, the history of the central limit theorem in geometry and hyperbolic geometry is very, very long, and I certainly cannot tell all of it today. For sure, there's a fundamental result by Sinai in 1960, and actually, I was just realizing that 1960 is 60 years ago, which is quite interesting, actually. But so he first proved central limit theorem, well, not for counting measure, but for the geodesic flow. So basically, you look at the invariant measure for the geodesic flow in, say, constant negative curvature, and then by Ratner in variable negative curvature. And then you take a function on your space. And usually, again, this function on your space has some nice property. For instance, it's usually Hilder continuous. And this is more or less the classical approach. And in fact, this was, of course, developed much more in detail by, for instance, people like Bowen, and then Lalin, Polycott, and many others. And for ANOSA flows, I mean, there is a very, very well-developed setting here. So what we're interested in is a bit of a more sort of discrete version of this in some sense, because we have a group action, and this is discrete group, and we're counting things in this discrete group. So we have both a discrete group acting, and also we have but we still have this manifold in which the group act. And so more recently, there has been more work also in this direction. So starting perhaps with Polycott and Sharp in '98, that somehow started comparing this hyperbolic metric with this combinatorial metric. And then there were many central limit theorems, starting with Horsham Sharp and Caligari and Fujiwara, and then Björklund and Hartnick, were considered certain functions on these hyperbolic groups. And one property that they did use, though, is that their functions are quasimorphisms. So the quasimorphism is something which is almost a group homomorphism.
Julio,
Yes.
There's a question in the chat line.
Yes.
Francesco wants to ask you something. You can speak up, Francesco.
I was just wondering if the previous CLT is some kind of adaptation of the Nagaev-Givarch technique with some kind of spectral gap.
So which CLT? The one we proved?
The one you proved, yeah, the one in the previous slide.
Not so much, actually. We don't use the spectral gap, actually, but we use somehow basically we use the Bowen central limit theorem just for shift space and the Hilder continuous function. I mean, there are more things, but we don't use that result. Yeah. More questions?
I guess you can continue.
Yeah, and then also kind of recently, slightly after we posted our paper on the CLM conjecture control, a student of Richard Sharp also proved the quite general central limit theorem on hyperbolic groups, and also, but also somehow for this distance function, or for this hyperbolic length. On the other hand, these theorems that are known somehow have the common issue that the action on the group on the space of the group on the space is still very nice. For instance, it's cocompact or convex cocompact. Depending on, I will throw some words from time to time, but for different people, maybe they will make more sense. But for us, we will consider a very general type of action, even though the group will be nice, maybe it's hyperbolic, but the action could be very, very bad. And in fact, we will see actions, for instance, on locally infinite trees and things like this. And for that, I don't think these techniques will, I mean, at least I don't see immediately how they would work. Okay, so, well, basic definitions. Okay, so we're talking about hyperbolic groups and hyperbolic spaces. So this everything is in coarse notion. So recall the classical definition due to Gromov that metric space is hyperbolic if triangles are thin. So basically, if you take 3 points, x, y, and z in the space, and you look at the geodesic triangles, so you look at the 3 triangles, 3 geodesics, basically, you have a side that basically there's some delta for which the side between x and y is contained in a delta neighborhood of either xz or zy. So this in a large scale, the space looks quite a bit like a tree in some sense, even though particular cases of this are definitely hyperbolic manifolds or manifolds with even certain variable negative curvature. So this could be adapted to the geometric setting. Okay, and then what is the setting? Well, the setting is that, yeah, we have X will be our space, and G would be basically group of isometries of our space, and you certainly will be finally generate group, and we will consider generating set S. And so again, we can define, we can think of G, for instance, we can think of G as a graph, because we can say we connect two group elements if their difference is in a generating set. And so this will give you a geometric structure on G, and you have a metric there, which is called the word length. And again, as I already mentioned, the word length is just the minimum number of generators that is needed to write your group element. Okay, and then again, and what is our sampling? Well, our measures will be basically, you have this notion of word length, and we take all the words of length n. And so this will be our sphere, combinatorial sphere, Sn. And then we're going to be interested in randomly picking elements uniformly in this sphere. So that's the definition. And also another word you will see sometimes is the translation length, which is basically, I call it tau because it's the same quantity as the length of the geodesic if I consider closed geodesic. But more generally, whenever you have a group action on a metric space, you can take this limit. So basically, you take powers of G, and you look at what is the drift of the displacement under powers of G. And this gives you a number which you can associate to this G, and it depends, of course, on the action. And but of course, you could be also just, if you're just interested in geodesics, well, this is just basically the length of the geodesic, which is represented by the group element G. Okay. And also another definition which sometimes will come up is element which we care mostly about are elements where this translation length is positive. And so they're called, in geometric group theory, people call them loxodromic, and probably you can, in terms of matrices, they're hyperbolic elements. So, but I will not say hyperbolic because otherwise there's too many hyperbolic things going on. So I would call them. And such elements, again, will basically fix a geodesic, so I have 2 fixed points on the boundary. And what we require about group is that it's non-elementary, meaning that basically it contains 2 such loxodromic elements that have disjoint fixed points on the boundary. So basically, yeah, you have at least this 4 points on the boundary, on the limits. Okay, so what is the statement? First, I'll give you sort of dry statement, and then I'll give you applications, and then I'll explain the definitions. And then if there is time, probably not too much, I will go into the proof. So basically, the theorem has just one hypothesis, which is, so we start with G, some finally generated group, and we want something good about the group with this generating set. And what the property we want is that it admits a thick bicombing. So I will be more precise later, but basically it means that this geodesics in this group can be represented by some graph, by some path in some finite graph. So again, still there is some coding in some sense. I mean, this is definitely not coding free. But also what we need out of this combing is not a lot in a way. So For instance, this graph could have more than one component, could have aperiodic components. I will give a precise definition later. But we have something good about the group, and basically we have no property, almost no property about the action. So basically G is a group of isometries of a hyperbolic metric space X, and it's non-elementary, so it contains two loxodromics, and that's it. So under these conditions, we can prove central limit theorem for what functions? Well, the functions we're interested in are two. So one is a distance. So basically, O will be just a base point in your space, and you look at the distance between O and its translates. So you take all group elements of length n, so Sn, remember, is that, and you count how many of them move the base point a distance, certain distance. And well, we say that the probability that such distance is minus n times L divided by square root of n is between A and B, converges to this Gaussian distribution. So that's precisely what is expected. The other function that we care about, as you could guess, is this translation length, tau. So again, in the very geometric setting, this is length of a geodesic represented by G, or it could be more generally this translation length. And we have a same central limit theorem, and in fact, with the same number L, so same drift, and same variance sigma. Where is the sigma? Sigma is here. So sigma is the same for both statements. Once you fix, of course, the action. And also we have certain rigidity, if you wish, or some condition that, again, is kind of traditional to figure out when you have a central limit theorem. You could have an actual very nice Gaussian distribution, smooth and everything, or sometimes in the degenerate case, you can converge to just a delta mass at a certain point. So if the peak of the distribution is very, very high with respect to the other the mass outside of the peak, then you can converge to delta mass at some point. However, this only happens in very special cases, and in particular, what we know is the following: that if this happens, basically it means that the geometric distance d and the combinatorial distance, which is this one, which is by double bars, they are the same in the following sense, that the geometric distance equals some number times the combinatorial distance plus a just bounded additive error. So this is a very strong definition. And in fact, basically in the geometric settings will imply that the length spectrum would be arithmetic. So basically that the lengths of closed curves would be all multiple of certain number. And that's, of course, a very strong statement. And so that does not happen in most cases. And somehow it's kind of studied when this happens. So this is, again, it's more or less what you would expect. Any questions about the statement? Is anybody still following? Maybe
no questions.
one person.
I keep my microphone actually muted, so that's why I have slow response times. Actually, there are some questions now.
Yeah, I'm asking whether it means that it's a graph. The third case.
It means that it's a graph. Well, certainly you can fudge a graph by some maybe finite amount, and it's still okay. So there is that. Maybe you could ask whether it's quasi-isometric to. No, I mean, the group. Yeah, I'm not sure. I think you can still fudge the graph a little bit and still keep this, but definitely this is very strong condition. Further questions, or?
In the meantime, yes, there's another question in the chat line. Sandrose, if you want to speak up.
I think Giulio just answered the question. Like, so for graphs, it's certainly true.
Right. So if a graph, yeah, that's right. So yeah, so Right. If the action is of the group on itself, yeah, that's true. Yeah.
Okay.
Thank you.
As a graph, yeah. Can I keep going, maybe?
So clear.
Yeah. Okay. Good.
Right.
Thanks for the sharing, because I can't see anything else other than my slides. Okay. So let's see. So so now I will present you 3 applications. There are maybe more, but so this is the first one is sort of more geometric in the sense that it's kind of closer to the say the Chas-Li-Maskit context, for instance, and other results that have been proven before. So remember that so one thing that we used in the previous approach was requiring that this manifold that we're looking at is nice in the sense that either it's compact, or if you know what it means, it's convex cocompact. So, but in fact, now with this new improvement, we can deal with other type of manifolds. For instance, manifolds with cusp. So actually, for instance, in particular, if you know what it means, so you can consider geometrically finite hyperbolic manifold. So quotient of the hyperbolic space by some discrete group, and somehow it could have cusps. Also, it could also have infinite volume, but as long as its fundamental domain is nice enough, basically it's a finite polytope, more or less. So definitely need not be compact, for instance. And if that happens, basically we can consider again the group, and this group need not be a hyperbolic group in the sense of Gromov because of this cusp, depending on the dimension. If it's in dimension 2, this group still would be hyperbolic, but in dimension 3 and high will not be. So this also is something that comes is new somehow. And then we consider again the length, and this length is just the length of the geodesic in the associated quotient manifold. So this is a classical geometric context, if you will. And so here we need some generating set. So unfortunately, we cannot prove this distribution result for every generating set. But at least what we can prove is that if you start with any generating set, you can enlarge this finite generating set a little bit to some other finite generating set. And then we can study that problem. So we can study the distribution of geodesic lengths in this geometrically finite manifold. So in particular, again, so here gamma is chosen uniformly at random in the sphere of radius n with respect to this other generating set. And so when I write this arrow means exactly that the probability that this number is between A and B is the integral of the Gaussian distribution. So n sigma signifies the Gaussian distribution of variance sigma. So this will be shorthand to avoid writing the same thing all the time. Okay, so in particular, let me add some remarks that are already written here. So first of all, it's already still interesting when the group is hard hyperbolic, and even though, because the action could be bad, even though maybe the group is a hyperbolic, but there are cases where you still have nice action which is a bit for instance, not convex cocompact. And in that case, we can take S prime equal to S. So we can do for any generating set. And in fact, for instance, this would be already further from the Chas-Li-Maskit conjecture, the case for surfaces of finite volume with cusp. Okay, this is easy case, and perhaps, I don't know how much is known about this. I don't think we could find direct result in the literature. So, but in any case, in this case, well, if it's in dimension 2, the group is virtually free, so it's hyperbolic. So somehow this is, in a way, nice setting, but this also goes to any dimension. And again, what is perhaps very important here is that this function, if you have a, say, geometrically finite action, so not convex cocompact, then this function that you're using as a function of the group is not Hölder continuous with respect to the usual. So if you have a coding with the space of paths in this in the graph, and then you look at this function, basically this function is not Hölder continuous, so you cannot really apply the usual scenario Ruel-Bowen machinery. Of course, maybe there are other things you could do, I don't know, but somehow definitely is not obvious. And again, in this case, we actually know, because we know that the length spectrum is not arithmetic. So basically, the length of all closed geodesics is, they're not all multiple of the same number. And so for that would imply that the variance we get is indeed positive. So in some sense, if you go back and look at the original, so somehow if you go back to the original experiments by Chas-Li-Maskit, which I won't know because it's too far back, but you remember that there were these graphs where basically when for instance one of the cuff's lengths is very small, then you will see that it's much harder to approximate the central limit theorem. I mean, it takes much longer for just the actual computer to do it. And the reason is kind of related to those, because in that case, the manifold does look more and more like a graph. So it kind of makes sense that it will take much longer to actually converge to the central limit theorem. We don't prove things about speed of convergence here. So of course, that's also a very interesting question, but on the other, at least we have this slight hint that this might be one of the reasons why it's different. So also again, so I remember that I showed you before. I showed you before a graph for self-intersection of curves. So now we can get some other application which is also in the same spirit. And it's the following. So you start with a hyperbolic manifold, and you look at the submanifold. So for instance, I'll show you a picture. You can start with a surface, and you look at the curve. So Chas and Lally just looked at self-intersection between the curve and itself, but we can also do similar thing, which is you take curve and you look at intersection of some geodesic with that curve. And in general, in higher dimensions, what you could do is you could take n manifold, n-dimensional manifold, and you can look at a sigma, which is codimension 1 submanifold. And so, for instance, if you have a 3 manifold, you get a surface. And if it's smooth and orientable and everything, you can define an intersection number between a curve and the submanifold. So how many times it intersects, basically, just geometrically. And maybe you take the minimum over all homotopy classes. And in fact, we can prove central limit theorem in this setting using this theorem that I showed you before. So basically, sigma here would be some submanifold, and well, it has to be non-degenerate in some sense. It's not fiber-like. So basically, M is not a fibration, basically. So it's like this, for instance, this is not a 3 manifold fibering over the circle or something like that. But if it's not fiber-like, so for instance, for curves and surfaces, this is always true, then we can look at fix. So you pick gamma. Gamma would be a word of length n in this graph, or in this group. And you look at the intersection of a geodesic, which is represented by gamma, which is with the submanifold. And again, we can get central limit theorem with respect to the uniform measure on the sphere of radius. So I realized that I didn't, so far there were not so many pictures. So fortunately, I have a picture of this application. So maybe you can be happy about that. So for instance, a case which is already interesting is when you fix an essential simple closed curve. So basically a curve which is not homotopic to trivial, or it's not homotopic to cusp. So for instance, if it's a compact surface. And so what's interesting here is that here really we need a more general type of action, because the action that we're considering, so this theorem is only about geometry. There is no, is about manifolds. There's not really a graph or something. But in fact, immediately when you see what the idea of the proof is, you will see immediately that you want to apply this to a case where the metric space you're looking at is non-proper. For instance, basically it's not locally compact. It's not finite dimension. So in fact, so here's the,
Sorry?
Yes.
How do you deduce this theorem from your original?
That's right. Yeah, exactly. So this I can show you, and I will immediately. So here's the main idea. So the main idea, for instance, for curves of surfaces, you consider what's maybe in geometric group theory is called the Basser tree, or I mean, similar construction exists in other fields. So basically, for instance, suppose your manifold is this orange surface, and your submanifold is this sigma, is this red curve. So, and then you want to pick a random blue curve and look at the intersection between this random blue curve and this fixed red curve. So the first thing is you take the universal cover of this surface, and the universal cover is the hyperbolic plane, H2. And then if you take a lift of this curve, you're gonna get a whole bunch of geodesics in the plane. And yeah, in this case, it will be this joint. And so basically you can this tree which is dual to this picture. And so here's what happens. So you can construct this this green tree. How do I construct this green tree? Basically, I pick a base point and I pick all these images under the group. So there is one point on each of these red curves. And then I connect them. And I get this green stuff. And this is a tree. It's dual to this well, lamination, if you want. So it's a tree, and in particular, it's locally infinite because, yeah, maybe it's not totally apparent, but there are gaps here, and there are more and more gaps. So so one vertex is connected to infinitely many vertices. This is the well-known construction of the Basser tree. And then your element, which is related to this blue curve, indeed, it lifts. There is a hyperbolic, there's a loxodromic element which translates this point to that point. And basically, what it does is it counts how many intersections there are. So basically, because from here to there, it crosses this red curve once, and another one is, well, the one you start with. So it's twice, which corresponds exactly to, in the geometric picture, to have these two intersections. So basically, the idea is that once you remove this red curve, and you can also remove the orange plane if you want, you have just geometric this graph, and this would be a locally infinite tree. And then you just look at the translation length on this locally infinite tree, and it turns out that the intersection number with this fixed curve is exactly the translation length in the dual tree.
Thank you.
Yeah, more questions about this? This is actually one of the things that are somehow easier to explain and more visual. So that's
no questions on the chat line so far. I mean, other than Clavis.
Okay, so I hope not everybody gave up. So encourage you to ask questions.
Still going strong. Lots of participants still.
Still, okay.
Not losing many.
Very good, very good. So by the way, I have 1 hour, right, until 12, basically.
Yeah, just about 1 hour, yes.
Another 15 minutes. Yeah, okay, very good. Okay, so this is the statement, and just for comparison, it's not quite the same as what Chas and Lally did, because they looked at self-intersections, but I didn't have my own picture because I was lazy, so I'm recycling the Chas and Lally picture for self-intersections. So, but the same phenomenon should happen. Okay, so now also let me tell you the third application. So the third application is just for hyperbolic groups. So so you can think of, so what is a hyperbolic group? Maybe if you don't know. So we thought we gave the definition of hyperbolic space. So when triangles are thin, and hyperbolic group is just a group such that when you fix a generating set and you consider its group as a graph, then this graph has the same property. So it has this hyperbolicity. And for instance, all this fundamental groups of cocompact hyperbolic manifolds are hyperbolic groups, free groups, surface groups. So there are several well-known applications. Okay, so now if you have a homomorphism between groups, what you could do is you can start. We can start. Sorry. Yeah, we can pick a generating set on G, and then you can pick another generating set on G prime. And now you can use the homomorphism to compare one to the other, right? And so what it turns out is that you can, if you start with picking randomly points on G with respect to this graph structure induced by S, and then you go forward, well, you produce a whole bunch of new group elements that have their own length with respect to the target space. And so it turns out that you have central limit theorem for this as well. So basically, if you take G randomly in the sphere of radius n with respect to S, and then you take the norm of G with respect to S, and then you have the norm of phi of G with respect to S prime. And so it turns out that you have also Gaussian for those norms. So so here, of course, it's not so complicated to see how it can apply. Well, once you know that hyperbolic groups indeed are some of these nice groups that have this thick bicombing, and I will explain a little more. But once you have that, basically here the action is just you take the action of G on the Cayley graph of G prime. So basically, by having this homomorphism, you can think of G acting on G prime, and so that's what immediately comes. However, what is quite interesting, I think, is that here we can also characterize the case when the variance sigma is 0, and this characterization is interesting, is in terms of what's called the Patterson-Sullivan measure. So there is a nice notion of measure on the boundary of these groups. So again, so you start with a homomorphism between groups, and then see if this is hyperbolic group. There's a notion of boundary, and which is similar to the boundary of, say, hyperbolic H2, which is you take all the geodesic rays based at a point, and then, okay, you can say the two rays are the same at infinity if their distance remains bounded forever. So there is a suitable notion of equivalence class. And in particular, you can put a measure on these groups and on it, well, measure on their boundaries, which is called the Patterson-Sullivan measure. And so basically what you do is the following. There are several constructions. So the easiest, so somehow the most explicit is you fix some S, which is some parameter, and then you put a measure on each of the elements in the orbit of your base point. So this is delta is a delta measure. And then you put some weight, which depends on the distance from the origin. So you weight the points which are further from the origin less. And then slowly you increase this number S. So eventually, basically, you create a measure. So this is a measure which initially lives on the group, but as you make S bigger and towards V, then this measure goes on the boundary. So this is a classical statement, which is called the classical construction, which is called the Patterson-Sullivan measure. And this limit does not exist, actually. So I wrote this limit, but it's cheating. In the geometric, so if you have it in, say, hyperbolic space, then the limit does exist. But in general, for a group, the limit may not exist. So you have different limit points. But all the limit points are in the same measure class. So they're all absolutely continuous with respect to each other. So you can talk about Patterson-Sullivan measure class. And so a consequence of what we did is the following, that in this theorem, we have sigma equals 0. So the variance is 0 for this homomorphism, for the central limit theorem, is equivalent to say that this homomorphism, first of all, it has to have finite kernel. So basically, you're not quotienting out too much when you go from G to G prime. And the second condition is that the Patterson-Sullivan measure class for G on the boundary of G pushes forward when you do this there's a canonical extension of this homomorphism from boundary to boundary, pushes forward to a measure class which is also the Patterson-Solomon measure class for S prime. So again, this is kind of not so common, does not happen very often. So here I realized that maybe it's a bit more technical for people who are not familiar with these measures. So maybe if there's any questions.
It looks like sigma is infinite when phi has finite image, right?
Well, infinite. So phi,
if you go back to the original statement.
Right. Yes. Yeah. Well. Well, yeah. You subtract n anyways, the length anyways, right? So.
No more questions on the chat line, though.
Okay.
It's not important.
Yeah, but anyways, yeah, when it's finite image, of course, it's very degenerate, the case. And yeah, we can figure out exactly. You may be right. I mean, yeah. Okay, so maybe in the next 9 minutes, I can, well, first of all, I have to give you at least the definition of what this thick bicombic means, because otherwise I gave you the main theorem without the hypothesis for the main theorem. And then, okay, very briefly, I mean, I have more slides with the explanations about the techniques and the proof, but of course, we don't have that much time. So I will be quite brief about that, at least give you some very brief idea. So first of all, again, we need some sort of coding. So what do we need? A graph structure. So what is a graph structure? Well, basically, again, you have some finite graph, and you fix a vertex, which you think of this as a starting vertex, so it's sort of identity. And then you want to say that every edge of your graph is labeled by a group element, or actually element in the generated set. So this way you can attach to each edge a group element, and also you can attach to each path a sequence of group elements. And also if you take the product of those, you're going to get another group element. So it makes sense to think about that. So again, this is also in the classical approach. For us, a very important object will be what's called the loop semigroup. So what is it? Well, basically, it's just the following. So in the graph, if you fix a vertex, you look at all the loops from V to itself. So clearly, this is a semigroup because you can compose loops between V and itself. And this will be somehow so we're going to bootstrap basically our central limit theorem, starting from a central limit theorem for sort of run and walk on this loop semigroup. So this is the first idea. And so we need this loop semigroup. So okay, and well, then what else do we need? What are the other assumptions we have? Well, so first of all, we have a graph. So then we have an adjacency matrix. And well, this graph has a leading eigenvalue. Again, this M need not be primitive, but and also this graph need not have only one irreducible component. And in fact, you might have more. But what we care about are the maximal components, so which are the components whose growth rate is as big as the whole graph. So basically, they have the maximal rate of growth. There's the most number of paths there. So first important definition that we need is the thickness of the structure. So what it means is the following, that basically if I start with gamma, so if I start with V, which is a vertex in the maximal component, and I look at gamma, gamma is this gamma V, is this loop semigroup. So this is a set of paths, and then we evaluate, so we look at it as a set of group elements. So this set of group elements has to be very big in a way. I mean, it's almost the whole group. So basically, there's a finite set B such that if you take a double coset, so every element of G can be written as B1 times some element which comes from this loop semigroup times B2. So this is a fairly strong condition, but in fact, it's satisfied for many interesting groups. And in fact, also it's interesting to note that this thickness implies what's usually known as almost summer simplicity of this matrix, means that, well, there could be many components, in fact, and there could be periodic components, but for every maximal eigenvalue, so for every eigenvalue of maximal modulus, its algebraic and geometric multiplicities agree. So somehow that part of the matrix is diagonalized. So, and then, yeah, so again, this is not, but need not be reducible and need not be hyperbolic. Also, another notion that we need is the notion of biautomatic structure, so which is the following. It's a bit of a pity that I can't draw, but I mean, I could draw, I guess, but it's a bit, I don't know if I have, I could try. I could try, but I'm not sure. Oh yeah, you see it, right?
Yep.
Okay, very good. Right, so yeah, so maybe I can show you this notion of yeah, I can draw a few things. For instance, the notion of biautomatic, I think it's much easier to understand if you can draw the picture.
And if you turn it sideways, we'll probably see it better.
Like this, right?
Yeah, that would be great.
Yeah, that's right. So right. So okay, so this is the definition, but right. And now let me add page. Okay. Right. So okay. So what it means? It means the following: that you have two paths. So H and G in the graph, and they have two elements, B1 and B2. And basically, what biautomatic means is the following: that if you have two paths that represents two elements in the group which are almost the same in the group, I actually can even draw here, it's even better. Yeah, so basically you have two paths a priori that you don't know much about, but you know that in the group there is this identity. So basically if you go G and if you do H, and you can do B1, H, and B2, and then it's the same as doing G in the group, then in fact the paths are close to each other all the time. So basically if you go along G for certain lengths, so here you have a G1, G2, Gi, and if you go along H for a certain length, basically this paths kind of fellow travel all the time. So that distance here is also not very large. So this is yeah, this is again, seems like could be quite strong situation, but actually it is satisfied for many interesting groups. So we will actually see. And in the end, so finally, to give this definition of thick bicombing is the following: that it needs to have this graph structure which has this thickness. So it's what we said before about the loop semigroup, and then also it's biautomatic, and also paths would be geodesic for this. Okay, so I think I have like 1 minute. Okay. So just let me say that groups that have this property, there are several, in particular, certainly hyperbolic groups, and much more tricky, which is related to this question of groups with manifolds with cusp, is that groups, fundamental groups of certain geometrically finite manifolds, which are relatively hyperbolic groups, they also have this property that have this thick bicombing, but you have to allow to extend a little bit the generating set. And then also right angle arcing groups, but maybe this is not so interesting. Okay, so maybe I will just abuse your patience for 1 more minute, just to give you just a very, very brief sketch of what are the main ideas, but very, very brief, is the following: that what is what are the techniques? Again, instead of using the classical coding and Hölder continuity, we use we go to this loop semigroup and we consider a random walk on this loop semigroup. And for that, we have, for this random walk, even if the action is bad, we have central limit theorems available to us due to Benoit-Comte and Horbès. And these are in general done for what are called central Volkow cycles. And then we apply this in particular to what's known as the Busemann cycle. So that's the first step. Then the second step would be to go from this loop semigroup to an actual Markov chain. And that's, again, that's some sort of suspension. So you consider some roof function and you consider some suspension. And Melbourne and Torak proved the theorem that says that if the central limit theorem holds for the base and for the return time, it also holds for the suspension. And then we have to approximate, this counting measure with this Markov chain measure. And again, there are some tricks which are based on you take a path and you basically considered some part of the path, you cut off some prefix and suffix, and you consider certain approximation. But I'm over time, so I really don't want to abuse your patience. So I think at this moment, maybe I will stop here. Thank you. That's Emile.
Okay, thank you very much. I think, Alessandra, if you can unmute everybody so we can actually give Giulio a big round of applause.
Scusami un attimo. Scusa un attimo.
And then maybe remute them.
I'm muting everybody, is not me.
Okay, if you want to ask questions, would you please book your time in the chat line? I have a question from Giovanni Panti.
Yes, may I speak?
Yes, absolutely.
Oh, the question is very simple. I just would like to know if the dependence of the variance and the mean, so sigma and L, are explicit in terms of the ABC, say in the case of the pair of pants, and for example, right. in the case of the sphere with 3 cusps, do you have the explicit numbers, sigma and L?
So the short answer is no. I mean, yeah. So basically, what we do is we reduce this counting in this setting to counting for random walks, and also for random walks, this question makes a lot of sense. The one you're asking, even for but in general, this is pretty hard to get explicit formulas. Even in the most concrete case, you have two 2x2 matrices or 4 2x2 matrices that you consider the pre-group generated by them. People try to work out bounds, but basically it's very hard to be explicit. What should be true is maybe that there is some analyticity that, you know, if you change your manifold a little bit, you should get a nice dependence on the maybe. But this also is not completely trivial. But to get explicit numbers is really hard usually.
So it is still unknown even for the simplest case, the sphere with 3 cusps.
Well, okay, maybe the most possible simple case. I'm not sure, because maybe if you go SL to Z and you have the simplest possible generator, maybe this has some number theoretic interpretation, but it's not going to be easy in any case. I'm not sure. I'm not sure if it's known in that particular case, but in general, it's really hard. Yeah.
Okay, thanks.
Okay, Giulio, actually, if you don't need the slides anymore, maybe you can actually unshare the screen so people can see your face. And there is a question from Dima Dolgopiat. Dima, you're next if you want to ask your question.
Okay, so maybe it was you have already answered something in the previous one, but still my question was, you showed in the slides that you have slow convergence when one over length is very small. Do you have some explanation of this? For example, what is the limit when one over lengths go to either 0 and infinity for this random walk which you have?
Right. Yeah. Well, I mean, yeah, we haven't. Yeah, well, I don't have a. Yeah, I definitely don't have a result on that. But I was just saying that if your manifold converge to graph, you would expect your variance to converge to 0. That was all I said. But you have to be precise about that.
But you don't have something which has 0 variance. You have something which is very like.
No, I do understand. Yeah, that's right. Yeah. So I don't know what the error term is. Of course, it would be good to have.
Any more questions? Or
But
maybe,
you don't expect like a different limit theorem when one of the cusps is like very small, for example, like 1 over n, where n is the length of it.
No, I think we can prove that the limit theorem is the same for all lengths.
Okay.
But the error term might be
Right.
maybe the constants in the error term or something. Yeah. Oh, there's more questions I see.
yes, there's a question from Steve Cantrell. Steve,
Right.
you may speak. Or I can read it.
Well, I see the question. Do you think a local limit theorem is possible? Yeah, good question. Yeah, I mean, what we use is this, somehow more general centered limit theorem for cocycles, and I don't know if there is a version of it which is the local limit theorem. I don't know, but it could be possible. Yeah, I mean, it's a natural question, but I don't know on the top of my head whether this has been proven in that sense.
Sure, thanks.
I mean, there's a local limit theorem for random walks. So, I mean, maybe
right.
You can adapt this. I mean,
Yeah, in the case that your graph only contains one component, so something like a right angle Artin group that doesn't split as a direct product, then maybe I'm wondering if when you're comparing between maximal components, maybe you lose a bit of knowledge. So if you only have one component, maybe, but yeah, I'm not sure.
Yeah, that's an excellent next project. Maybe we can work together.
All right. Any more questions?
I guess I've got another one if that's all right.
Yeah, absolutely. Go ahead.
Brilliant. So your third application to your CLT, which was this comparing, or it was a CLT for this homomorphism between hyperbolic groups. I think in your paper you mentioned that this would imply the central limit theorem for stuff like the abelianization homomorphism, but I just couldn't quite see why that was the case.
Oh, I don't think we said that. I think we say
okay.
that
Maybe
there is a theorem like that. I mean, of course, you know, if you take a value to z, that there is one thing. Of course, abelianization is with values in zk, and so it's not completely trivial. Yeah, I completely. Yeah, I'm not. Yeah, I don't say that it follows completely immediately. Yeah.
Cool. Thanks.
All right. Any more questions?
So how do you compare word length and the translation distance? So the proof scheme you presented seems to work for cocycle, and then how do you go to word length and to translation distance, etc.?
Right. So you start with Boseman cocycle. So of course, I assume you know the definition of Boseman cocycle, and then from there you prove that the Boseman cocycle is close to the displacement, and that's not that hard. I mean, yeah, this is already done by Horbes, for instance, and then from there, and then if you want to do translation length, well, you know that translation length is equal to the displacement minus 2 times certain Gromov product, and then you prove that this Gromov product, which has to do with basically whether the axes are aligned or basically the axis of G, the axis of G inverse, maybe they're aligned or not. And I mean, but we have this technique that we've done several times that basically show that that the axes of G and G inverse are almost always aligned. So basically, this third term is always very small. Actually, no matter how small you want it, it's going to be smaller than that.
Okay.
So there's that. I mean, of course, it takes more time to explain more details.
No, but thank you.
All right. Any more questions or comments or anything? Seems not. So thank you very, very, very much, Giulio, on behalf of all of us. Lots of virtual clapping, as you can see from your screen, I guess. We won't open up the mics anymore, I guess.
I guess there was a question which we forgot, which is whether it works for higher codimension submanifold. Well, I certainly don't know how to do that. Yeah.
I guess I missed it.
Yeah, I certainly didn't know how to do that. Yeah.
All right. So once again, thank you very much, Giulio. Thank you to everybody who participated here for the questions. It's been a very nice first attempt at this DinAmicS One World seminar, in a sense. And there is a seminar next week, same time, by Martin Legil. And then we have seminars every Thursday at 5 p.m. Central European Time. Thank you, everybody. And thanks again, Giulio. I guess we can stop the live broadcast here.
Okay, thank you.